So I call my mom for advice a lot. My mom is an elementary school music teacher in South Florida. She also has a PhD in organizational psychology. And I was talking to her about my TEDx talk, and I was going over the points I want to make, that physicists are regular people too, and that this is a field that's it's creative and it's really screaming out for more diversity. And so I was bouncing some ideas for titles off of her, and she interrupted me and she said, "I've been reading this great book called The Sociopath Next Door." Well, today I'm going to tell you about the particle physicist next door. So when I go out and I give public talks on particle physics, I get a lot of great science questions afterwards, but invariably I also get questions. People come up to me afterwards and tell me how surprised they are that I look the way I look, or that I act like a regular person, that I walk and talk and act like I do. And I'm not surprised that I'm more or less a regular person, but people in general that I meet outside of my workplace are. And I think there are a couple reasons for that. One reason is that people really don't understand what it is that I do. So what is it that a particle physicist does? And we're going to start with something that's a little bit more basic to lead into that. What is a particle? So we're all made of molecules. The Earth is made of molecules. And molecules are made of atoms, and atoms have a nucleus with electrons orbiting them. And I'm concerned with the particles that are even smaller than that. So if we start inside the nucleus, you may have heard that the nucleus is made of protons and neutrons, and it's orbited by electrons. And you're all able to watch this presentation right now because of particles of light called photons. Turns out that protons and neutrons are not fundamental particles. They're actually made of other particles, and those particles are called quarks. Protons and neutrons are made of up and down quarks. And the up and down quarks inside a proton or neutron are held together with gluons. Makes sense. So in addition to the electron has negative charge, right? There are two more heavier guys that act pretty much the same. They're called the muon and tau. And the electron also has a lightweight neutral counterpart called the electron neutrino. And so do the muon and tauons. Now, there are three generations of these you can see. There's electron, muon, tau, and their neutrino counterparts. And there are three generations of quarks, too. So in addition to the up and down quark, we also have the charm and strange quarks, and the top and bottom quarks, also called truth and beauty by some. So these are almost all the particles that we know of. There are a couple more, two more force-carrying particles, kind of like the gluon, and they're called the W and Z bosons. And this is what we refer to as the standard model of particle physics. Now, in order for all of this to make sense, there's an awful lot of it there, but in order for all of this to make sense and for the particles to have the properties that we know they have, like mass, there's one more thing that's needed, and it's probably something that you've heard of. It was in the news an awful lot this summer. It was the Higgs boson. So the Higgs boson was discovered this summer at the Large Hadron Collider, which is a particle collider in Europe at CERN, which is the European Center for Nuclear Research. And this made news all over the world. It was on the front page of tons of newspapers. It actually even made it into Sports Illustrated, though it did not make the cover page. So now the Higgs boson has been discovered, and everything we know about particle physics sort of makes sense, but not quite. The LHC is looking for a lot of other stuff, too, because there are more particles. Everyone's pretty sure there are more particles than just the ones I've shown you, even though that's quite a few already. So one reason that we know we need more particles is because most of the mass in the universe can't be explained by any of the particles in the standard model. So this is what's called dark matter. It makes up about 84% of the mass in the universe, and we have no idea what it is. Well, we have some ideas, but we don't know yet. So the LHC is looking for dark matter. It's also looking for lots of other types of particles. But what goes on at the LHC? Who works there? What do they do? So this is my friend Taylor. Taylor works at the LHC. He is an experimental particle physicist who works on the ATLAS detector, which was one of the detectors that helped to discover the Higgs boson. And Taylor leads a pretty normal life. He's from Kentucky. He was also the best man in my wedding, I should say. He's from Kentucky, and he and his wife are both American, but they live in a small town in France and have 2 kids. Taylor gets up in the morning, and he goes to work like a regular person. He takes his son to CERN with him because his son goes to kindergarten there. And Taylor goes to his office, and he answers his emails. And throughout the morning, he'll probably work on his project, which is an analysis of the data that's being collected at the LHC. That analysis involves tons of data, so this is lots of computer programming. Now, at ATLAS, the experiment that he works on, things are controlled from this room. This is the ATLAS control room, and there's a ton of stuff going on there. The particle collider operates 24 hours a day, 7 days a week, and so there's a person who's sort of designated to be in charge of what's going on for a 7-day shift. And so if Taylor has been the run manager for a 7-day shift, on call 24 hours a day, he'll have to write up a report each morning about the details of every single thing that happened in the day before. So Taylor will take his son home for lunch, and when he comes back at the end of the day, maybe he'll do a little bit more analysis, or he will attend meetings. These are huge collaborations, thousands of people, and so it takes a lot of meetings to keep everybody on the same page with what everyone else is doing. So Taylor's day ends at about 5:30, and he'll go home, or maybe he'll stop off for a beer with his friends at the CERN canteen, which is right on campus. And my life is not so much different than Taylor's. I'm a theoretical particle physicist, so I don't work at a collider. I don't have a control room. I do have a classroom, though, so I get to teach. And I don't work on projects for a big collaboration. I get to choose my own projects, which often involve pencil and paper calculations, but they also involve computers. So I spend a lot of time writing, and I spend a lot of time generating data, and having new ideas, and figuring out how to analyze that data and how to show it to other people. So here's a not particularly good picture for other people, but it's a picture that really excites me. This is an example of models that I work on in supersymmetry. And so all of these colors probably mean nothing to you, but when I look at this, I see a whole lot. So what I see is that this is a model that can explain the Higgs boson. This is a model that agrees with everything that we know about particle physics. And this is also a model that can explain all of that dark matter in the universe. That's what's happening actually in the turquoise region on the right. So I see this and I get very excited. Now, you might be starting to think that the work that I do is creative, and it is. We have to work within a set of constraints, that is the physical universe around us, right? And we have to think about how we can solve problems, like what is the dark matter? And there are lots of other problems in particle physics, too, that we want to solve. And ideally, you have a theory that, when you think of a new idea, you propose a theory that can solve multiple problems. And then you want to go out and ask, how can we figure out if this is the right theory? So how do we know that this theory is true? And actually, equally importantly, how can we ever know that it's actually not true? Being falsifiable is really important, too. Another question is, if this theory is true, what will we see at the LHC? Will there be new particles copiously produced, and what will they look like? And is there any other evidence? Use your imagination. Could we look through telescopes to see evidence of this new theory, or maybe use satellites in space that are making observations? So all of this, thinking through this process, having the idea, working within the constraints, and thinking through this process, these are all creative things. These are using your creativity. And because this is a creative enterprise, this is one of the reasons why we really need more diversity in the physical sciences. Diversity in the workplace breeds diversity of solutions. So I am a female physics professor. I'm a lot of things, but I'm also a female physics professor. In the United States, at PhD granting institutions, only 12% of faculty members are women. So why so few? This is a question that's been asked throughout the ages. And there are a ton of reasons. Most recently, there was a study commissioned by the American Association of University Women, and they found that they could sort of categorize this into 3 reasons why there are so few women in the physical sciences. First, societal beliefs and the learning environment for young children often discourages them from continuing their interest in science. If you manage to make it past that, and you're still interested in science when you're a grown lady, you end up encountering implicit bias everywhere. Even people who actively reject stereotypes all have implicit biases, and so it's important to learn that about yourself and learn how to handle it. There's a third reason, too, and that is that dissatisfaction with the academic workplace disproportionately affects women. And part of the reason is because of ineffective or bad family leave policies or things like that that disproportionately affect women and cause them to sort of leak out of the workplace faster than their male counterparts. Now, in my daily life, I am sitting at my computer usually, and I don't really feel like my life as a female theoretical particle physicist is that much different than it would be if I were a male theoretical particle physicist. But there have been issues and situations that caused me some sort of special consternation as a woman. And a very innocuous example of this is something that happened last year when I was a first-year faculty member at the University of Utah. So there are these winter schools and summer schools for graduate students, where graduate students go for a week or a couple weeks, and they have very intense courses on advanced topics that they wouldn't learn otherwise at their home universities. And so I was invited to lecture at the Cosmology on the Beach workshop, which is it's jointly sponsored by the Berkeley Center for Cosmological Physics and the Institute for Advanced Cosmology in Mexico. And it's a fantastic idea. It's attended by students from all over the world, primarily from the Americas, but students from all over the world. And so I was invited to lecture, and I'm first-year faculty, and I'm thinking I have to be a great role model for these graduate students, and I have to make a good impression on my more senior colleagues who are also lecturing there, because a lot of them probably didn't know yet that I had jumped up into the faculty bracket. So I was thinking about all of these things and how I want to portray myself, and I was also struggling with the decision of whether I should wear a one-piece or a bikini. So I wore the bikini on my mother's advice. I'm coming untaped. I wore the bikini on my mother's advice, and everything worked out fine. The world did not end. And that's not to say that issues that women face can be boiled down to the choice between a one-piece or a bikini. There are very real issues, but there I was on the beach in Mexico in my bikini, and we're swimming and we're playing volleyball, and I wonder if the people that were at that resort as tourists, I wonder if they even noticed that we were physicists. I bet they didn't. I bet they thought we were just a bunch of regular people. Because we are regular people. We're regular people who happen to have really cool jobs. But in order to start looking more like regular people, we need to improve the diversity. We need to improve the representation of women and minorities in the physical sciences. Now, most of that has to happen in the workplace, as I showed you those 3 reasons that the AAUW found. But there are some things that you can do. Elementary school kids, when they enter elementary school, boys and girls are equally excited about science. No difference between boys and girls. But it's the societal beliefs and the image and the perceived lifestyle that eventually disproportionately turn women away from science. No, we don't all wear lab coats and have pocket protectors and broken glasses, right? So what can you do? I'll finish by asking you to think about yourself. Think about your preconceived notions of what you think a scientist is. I want you to question, and we all have preconceived notions, I want you to question the origin of those preconceived notions. Yes, physicists have demanding lifestyles, and it is a job that requires extensive academic training. So it's not for everybody, but it should be proportionally inclusive. Physicists have hobbies and families and friends and neighbors, and we need your help. We need your help to improve diversity by one essential step, and that is to shake off those preconceived notions so that we can change the face of the future physicists next door. Thank you.